So I'm David, and in this talk, we want to make sure that people understand what graph databases are, specifically what Janus Graph offered out Compose is, how you can use it in the best way possible, and how Scylla fits into that larger picture as a whole. And we even do some comparison to the service that we offered that used Cassandra, as compared to the one that uses Scylla. Welcome to our talk, Stretching Scylla Silly. Try saying that a bunch of times fast. So in this talk, we're going to talk about the lay of the land of graph databases. We are going to talk about what it takes to run a highly available hosted cloud solution while giving users a seamless horizontal and vertical scaling solution. And we will talk about our experiences migrating from a Cassandra-backed solution to one backed by Scylla. So my name's David Patera, and I am a contributor to Tinkerpop and Janus Graph. I work on IBM Graph and Janus Graph on Compose, and I've been working on graph databases with IBM now for about 1.5 years.
My name's Keith Loans. I've been working on IBM Graph and Janus Graph on Compose for about 2 years, working in that whole ecosystem. I'm also a contributor to Tinkerpop and Janus Graph.
So now we're going to talk about our platform, IBM Compose. So IBM Compose is a platform for hosted open source databases. It enables easy and sometimes automatic scaling, which can be horizontal and or vertical depending on the use case and database. He's telling me to slow down. As a platform, we offer 24/7 support and operations for all the databases. We allow you to get information about your databases through a monitoring and logging infrastructure. We take automatic backups and snapshots of your data and offer the ability to do that upon request and with the ability to restore that data into another database. It's available on compose.com and on IBM Bluemix. And the databases on the platform range from Mongo to etcd to Scylla to Janus Graph to Redis, etc.
So I want to go over just a little bit of background on graph databases. We're going to go over what is a graph database. We're going to go over what Tinkerpop is, and we're going to go over the components of a property graph. So a graph database is a database that enables storing data on highly interconnected set of vertices and edges, both of which can have properties. This is enabled through Apache Tinkerpop. And Apache Tinkerpop is a framework that manages the query and management layer of graph databases. So now I want to talk a little bit about the components of a Tinkerpop, specifically property graph. So the first class citizen in a graph database is the Vertex. It is the only first class citizen in the Tinkerpop property graph model. A common mistake that I see, working on a managed service, a lot in support questions around modeling and things like that, are folks treating vertices and edges as first-class citizens of the property graph model. They are not. So vertices like this can have a label. This one is a person. It's kind of akin to a type. And vertices are connected by edges. Edges are a second-class citizen in the Tinkerpop graph property model. And they can have a label, and they can have properties. Those properties are restricted to key value pairs, and those values cannot be lists or anything like that. So these properties, these key value properties, are a third-class citizen to the Tinkerpop property graph model. Vertex properties are kind of a special case. Vertex properties are kind of akin to edges, there's kind of in this hierarchy of elements that you can have in a Tinkerpop graph. They're kind of second-class citizens too. And the way that I like to think about why that's the case is because both represent a binary relationship between another set of data. So you can see here, the person, Keith, lived in Brighton and Boston, and David lived in New York City and Boston. This is different from the properties that you can have on an edge because they can have a higher cardinality than just one. You can have a list or a set be the value of this property. Vertex properties are also unique in that they can have what's commonly referred to as meta properties. So here you can see I've added some meta properties to the lived-in values. So for the person Keith, I lived in Brighton from 2010 to 2014, and I lived in Boston proper from 2014 until now. They're not mandatory fields on the value by any means. I have no clue when David actually moved from New York City to Boston, so I just didn't put it on the slide. So querying all of this is enabled through Gremlin. Gremlin is a universal traversal machine. What does that mean? It means it's Turing complete. It's very expressive. You can express these properties in lots of ways. It's not just querying, it's also moving a bit through your sets of data. So sort of moving through subsets of vertices via edges. And it looks a bit like this. So you start out, g.v is your entire set of vertices, and then you filter on age. In this case, there's 4 vertices that have that age. And then this is where the actual concept of traversing comes in, with this outstep that follows after that. The outstep means to move in the out direction. Edges in the Tinkerpop model are directed. And move to that set of vertices. So you can see that you've now moved from the set of vertices that has ages outward. And then it's filtering again on vertices that have the name, Vatis, and Josh. And there's a whole bunch of these types of steps. You can query on edge properties, edge labels, all sorts of different steps to be able to move around to different sets of data.
Okay. So now we're going to talk a bit about what exactly is Janus Graph. So at a high level, Janus Graph is a Tinkerpop compliant graph database implementation. This is a list of companies that are either using Janus Graph in production or are contributing to the open source project. I forgot to put IBM's picture here. So this is a picture of the high-level architecture of the Janus Graph system. So the first big draw to Janus Graph is the fact that it supports pluggable backends. The current supported implementations are Cassandra and therefore Scylla, HBase, BerkeleyDB, as well as DynamoDB and Bigtable. The reason that this is nice is that it allows you to choose where on the CAP theorem spectrum you prefer to lie. For example, HBase prefers availability over consistency. And at Compose, we're focused on the OLTP side of this diagram. And Janus Graph is pretty new, but the code behind it isn't. So there's a bit we should understand in history there to understand more about the project. So in February of 2012, which is like 5 years ago, we see that Titan Graph database was started by Aurelius. 3 years later, that was acquired by DataStax. A few months later, Titan 1.0 was released. And then we see that nothing happened to the Titan project after that in the open source world. A lot of companies were already using the open source project and really upset about this, the fact that it just kind of died. So, you know, a few people from a few big companies like Google, IBM, etc., got together, forked Titan, created Janus Graph, and made it an official open source project at the Linux Foundation. And then, fast forward, it has its first release, and then the second release, 0.20, was released 2 weeks ago. So if we go back to this picture, the other draw to using Janus Graph, other than just pluggable backends, is the fact that Janus Graph is very easily horizontally scalable, and again, that's the OLTP side of this diagram. And this scalability really is the main draw to Janus Graph as opposed to any other graph database on the market. Now I want to tell you guys a little bit about how you could use the system in the most performant way, and of course that's through the use of indexes. So Janus Graph supports multiple types of indexes. We have composite index, mixed indexes, and vertex-centric indexes. Now your mixed indexes require a separate backend, and those are the indexing backends like Elasticsearch, Solr, and Lucene. And through the use of these indexes, you could do things like full text searches and geolocation type searches. Composite indexes are exact match lookups, and those are the typical indexes you would think of when you think of a database index. And finally, Janus Graph supports something called a vertex-centric index, and these are kind of the Janus Graph special sauce. So a challenge in graph databases is when you have a node that has, a ton and a ton of incoming or outgoing edges. And these nodes are usually referred to as supernodes. And vertex-centric indexes allow you to create an index on a per vertex basis based on an adjacent edge's properties, which allows you to basically pull smaller subsets of data in as you traverse along your graph. That might have been confusing, so let's go over kind of an example of a few traversals that would allow you to use a composite index or a vertex-centric index. So let's say we have data storing people, products, and products that specific people buy. So it's probably going to be the case that we want to retrieve information about users based on their name. So like the first traversal here, g.v. has name Keith. So it probably is going to be a good idea to have create a composite index on the property name. So that index, that query, that traversal would use a composite index. But what if we wanted to know all the products that people buy? And what happens if someone bought over 100 million products, right? That traversal would be pulling into memory 100 million of these elements or more. So it may make sense in this case to only return the last 20 elements that someone has bought. So we can use a vertex-centric index that would retrieve a result ordered by the timestamp property on the bought edges. So if you look at the second traversal, that's exactly what we're doing here. And that index, that query would make use of a vertex-centric index.
So at this point, I hope we've laid a decent foundation for what Tinkerpop is, what Janus Graph is, what graph databases are in general. So now I want to talk a little bit about Scylla and Janus Graph. Specifically, I want to go over, how exactly does Janus Graph store data in Scylla? So this is the Janus Graph backend data model for vertices. Each vertex has a unique ID that stores an adjacency list. So that's your properties and your edges. And if you think back to what I was talking about vertex properties and edges both being second-class citizens in the Tinkerpop property graph model, this makes complete sense, right? They're right there, right next to each other. So each cell in that adjacency list represents a property or edge. And the only other constraint that Janus Graph has on the back end, other than obviously supporting this key column value store kind of big table type model, is that these cells must be sorted by column. Column. So this is the, oops, sorry, that's the wrong button. This is the representation of non-first class citizens or properties and edges. So edges are kind of stored as shown. They have the label ID plus the direction. And that kind of plus direction, it's literally just the last bit. They add an extra bit on there, 0 or 1 for in or out. A sort key, that's defined by the vertex label, or what key you're going to sort on in the edges. The adjacent vertex ID, you got to somehow move to the next vertex, right? And finally, the edge ID. And then the signature key and other properties are stored in the value. So the blue boxes in this photo are stored with a variable length encoding to save space. And the red boxes are basically store one or more property values. And the gray boxes are actually the uncompressed property values themselves. Property storage is simple, quite a bit simpler than actually storing that edge. And it's the same color encoding there on the chart. The only thing that isn't shown here, and I talked about it a little bit before, is that you can have properties on vertices that are sets or lists, and if that was the case, then the property value, the property ID would also be stored in the column.
So Scylla really is a great fit for Janus Graph on Compose because it's fully Cassandra compliant, which means it's fully Janus Graph compliant. And two, and probably more importantly, it's easily containerized because it's extremely lightweight. Our team has operated and supported a Titan/Cassandra system for 2 years. So we recently, in April, unveiled the production-ready Scylla-backed solution on Compose, and we've had no problem loading large data sets. The tooling to support Scylla has been great, and overall, we've been really happy with the performance of the Scylla-backed system. Needless to say, we had a few issues with Cassandra, and most of these had to do with Cassandra configuration options, hitting thrashing issues, tuning the garbage collection, things like that. And in comparison, we have only filed one issue against Scylla in our current repository. And the fact that we've been running a production-grade database system since April, backed by Scylla, and we haven't hit many issues, honestly speaks volumes to the success we've seen using Scylla. We have been successfully scaling our Scylla nodes, maintaining the nodes, upgrading the nodes, migrating data between the nodes, and it's been great. And in comparison to our Cassandra system, where we did hit a lot of issues with configuration tuning and garbage collection tuning, we've been really happy with Scylla. Mandatory slide, and thank you.